Okay, so before we begin, are there any questions from last time or on the homeworks or the course in general? Okay, so if there's no questions, then let's go ahead and start reviewing a little bit about what we talked about last time. So we introduced the definitions for the Fourier transform. We started off with the 1D Fourier transform and have these definitions here. So the forward transform here and the inverse transform here. And so we will do, a lot of 1D transforms just because they're a little easier, but eventually we want to work up to doing 2D transforms. So these are the definitions for the 2D transform, and essentially just going from a single integral to double integral. As we noted last time, we're going to use kx and ky because that's pretty much standard for a lot of the literature. The book uses u and v, so you'll just have to sort of make that transposition as you're reading through the book. Yeah. Oh, yeah. Great. Okay, so so basically the notation here, so you can see that there. Okay, so let's review some of the transform pairs we did last time. These are basically, I just took these from the sort of a cheat sheet for last year's exam, and so these are essentially some of the elements that, especially for exam 2, that you'll certainly be responsible for, and potentially some on exam 1 as well. So really, these are really the key transform pairs that come in really, really handy throughout the course. And so it's pretty good. It's a good idea if you sort of commit these to memory and get used to working with them. So for example, last time we talked about Dirac delta going to 1. And we also talked about duality. If you know the Fourier transform going one way, then you sort of know that 1 goes to the delta function. So that's an example of duality. Okay. We also see duality here. Okay, so that's a dual pair. So rect goes to sinc, and sinc goes to rect. So that's good to know. And then we also see duality here, where a shifted delta function goes to a complex exponential with a minus sign. But then without the minus sign here, that's a plus sign, that goes to a shifted Dirac in the k-space domain. So that's the only one where you sort of have to sort of keep track of that sign. Okay. Then the other really useful transform is what's the transform of a cosine or a sine, and these turned out to be the sum of Dirac delta functions. Okay. So for example, a cosine, you should be able to just look at and see. So for example, if I have cosine, let's say 8 pi x, then I would rewrite it right away as cosine 2 pi 4x. Okay. So I can identify this as being sort of my frequency. And then on the Fourier domain, I would just draw it like this. 1/2 frequency of 4 and minus 4 1/2. All right, so you should be fairly comfortable with something like that. We talked a little bit about this, separability, so we'll go over this in a few slides. And then today we'll also go over this one. And then we're not going to get to sampling today, so we'll have Professor McVeigh cover that probably when he talks about sampling in CT. And at that point, we'll cover this. So this is going to be when we talk about sampling. Okay. And then here on the right-hand side, we've got some useful definitions just for your reference. Okay. So we've defined the sinc function, the 2D Dirac delta function, a two-dimensional sinc function, two-dimensional rect function. Today we'll cover this one, the triangle function, and last time we covered what happens when you have a scaled Dirac delta function. Okay, so these are just sort of things that are useful as you're doing the homeworks. Okay, any questions on that? Okay, and also the book sort of has a similar table now in 2D, so the basic idea is the same, but you can take a look at that table at your leisure. So let's just sort of start off by reviewing some of the properties. So we'll start off with one that we talked about last time, which is if a function g of x, y, can be written as a function of x multiplied by a function of y, then the Fourier transform g of kx, ky is simply the Fourier transform of the function in x multiplied by the Fourier transform of the function in y. Okay? So that's useful to know. Now, one common mistake people sometimes make is they might say, if I have a function g of x, and I can write it as two functions of x, it's tempting to write that as the Fourier transform as h1 kx, h2 kx. Okay, but that turns out to be not correct. Okay, so that's not the separability function. Okay, so it has to be, this has to be the x, this has to be the y. Okay, they have to be two different variables. So the example of this, which will come up quite a bit for the rest of the class, is if you have a two-dimensional rect function. So you have something like this. So it's 1 here and 0 everywhere else. It's separable, so I can take the Fourier transform of this rect, which is just a sinc, and then I can take the Fourier transform of this rect, which is another sinc. And so I just get the product of two sinc functions. Okay, so that comes up a lot, and this is what it looks like. So we have our rect function here, and then this is the product of two sinc functions. Okay, so it's obviously much easier to do it in MATLAB, but if you have to draw it by hand, it's acceptable just to do something like this. All right. Okay, any questions on that? Okay, so that's pretty much review. Now let's start talking about some properties we didn't go over last time. So the first one is linearity, and the nice thing is the Fourier transform is linear. So if I have two functions, say g and h, I multiply them by scalars a and b, and I add them together, then the Fourier transform is simply the Fourier transform of g, which is g of kx, multiplied by that scalar, plus the Fourier transform of h of kx multiplied by its scalar. Okay, and then I add them together. All right? And the same thing, so this is for 1D, and the same thing applies for 2D. Okay? So let's go through an example of that in 1D. So here I have a function, it's g of xy. So notice I've defined it as a 2D function. Okay, even though it looks like there's only one dimension in the definition, I'm explicitly defining it, saying this is a 2D function. Okay, so this is equal to 1 plus e to the minus j 2 pi ax. Okay, so when I see something that's defined as a 2D function, I should probably rewrite it as 1 plus e to the minus j 2 pi ax times 1, where the 1 is sort of in the y domain. Okay, so this 1 we know in either 1D or 2D just goes to a Dirac delta function. So that's easy. Okay, but this one here is now a separable function. Okay, this term here is a function of x, and this term here is a function of y. Okay, so then what I would do is I would write this is equal to plus the Fourier transform of this. Okay, so that's e to the minus j 2 pi ax. So I look at this term, e to the minus j 2 pi ax. That's telling me that there's a complex exponential with a frequency of a. Okay, and the frequency is actually at minus a. That's the frequency. Okay, because of this minus sign. All right, and therefore I write it as, it should be a Dirac, I should have a Dirac delta then at minus a. All right, and so that's just delta of x plus a. Sorry, it should be kx. Let's erase that. Okay, so then I get this plus delta kx plus a times the Fourier transform of 1 is just a delta function, delta ky. All right, so that, and then the second example is essentially the same thing. It's just this function of y. So you might want to look through that and just convince yourself that this is the correct answer. Okay, so that's how you apply linearity. So what we've actually done is we've applied linearity and separability. So we've actually applied two properties. Okay. Any questions on that? Yes.
Just real quick, how do you get only the ky out of that second times 1?
Yeah. So this 1 here is my implicit function in y, and so we know that 1 goes to delta ky if it's defined as y. So this is a function of y. Okay, so 1 always goes to a delta function, and if it's just And then the ky comes because we've implicitly assumed that it's a function of y.
Yeah, I just meant the assumption thing.
Yeah, yeah. So basically, because the problem is telling you it's a function of x and y, that means that if you look at the function, there's no, let's see, let's bring in another color. In the y domain, see there's no variation, right? So that's why there's that 1 in the y dimension. Yeah. And all the variation is in the x domain. Okay? Sure. Okay, any other questions on that? Okay. Okay, a super useful theorem is the scaling theorem, which means if we take a function and we just scale its argument, say make a g of ax, then the Fourier transform is big G of kx over a, 1 over the magnitude of a. Okay? And same thing, similar thing applies in 2D. So let's do, and this comes up all the time because we're always starting off with a rect or sinc function and then scaling it to the dimensions that we want. All right? So let's take a really simple example. So we know that rect of x goes to sinc x, right? Sinc of kx. So we know that's a Fourier transform pair. Okay? So now let's look at rect of 3x. Okay, so that's going from here to here. And so I'm multiplying by 3 in the argument, so I'm shrinking things. Okay? So now this had width of 1. What's the width of this guy going to be? So I've shrunk it by a factor of 3, so what's its width? 1/3, right? Okay, so it's got a width of 1/3. Okay, so by the scaling theorem, I just take the 3, I take 1 over that, magnitude 1 over 3, and then I have the sinc function, and then I have kx over 3. Okay, so that's going from the sinc to now this is at 1/3, and you can sort of see the distance between zeros has gone up by a factor of 3. Okay, so this is a really important thing about the scaling theorem, which is it tells you anytime you shrink in one domain, you get wider in the other domain. Okay, so you want to keep that in mind as you're trying to do sanity checks on your answers. Did it go the right way? All right. We already sort of saw this before when we talked about the modulation transfer function, where we looked at different LSFs, or these are basically my impulse responses. And we noticed as the impulse response got broader, so it's getting broader here. Okay, this is essentially, the MTF is essentially a Fourier transform of these impulse responses. So as these get broader, these get narrower. Okay, so that's just an example of the scaling theorem that we already talked about. All right, so that's good to keep in mind, that this intuition, as things get narrow in one domain, they broaden in the other domain. Okay, the main thing we're going to talk about today is the Fourier transform of what happens when you convolve two functions and you want to know what this Fourier transform is. So I'm just going to tell you the result first, and then we'll sort of give you a sort of a intuitive explanation of why it's plausible that it's true. So essentially, we want to know the Fourier transform of g of x convolved with h of x. Okay, and the answer is simply it's the Fourier transform of the function g of kx multiplied by the Fourier transform of h of kx. Okay, and so this is when this operation is convolution. All right, and similarly, if I have two functions g of x times h of x, I have to convolve their respective Fourier transforms. So now this is convolution. All right, so that's just the result that you'll find very useful for the homework. And let's take a look at trying to understand why this might be true. So let's assume we have some function g of t. Okay, so this is the function here. And in this case, it's composed of 3 different frequencies with different amplitudes. Okay, this might have frequency f1, amplitude a1. This might have frequency f2, amplitude a2. This might have frequency f3, amplitude a3. So we could also describe it in the Fourier domain as this is f1, f2, f3 with the amplitude a1, a2, and a3. Okay, so we've already talked about that before. So now let's imagine putting these through, and we're going to assume that this is a linear shift invariant system. Okay, And what we're going to say is that this has some impulse response, h of x, or h of t in this case. And then the Fourier transform of that is just h of f. Okay? So that's the Fourier transform. So I can have an impulse response of my system, and I can also have its frequency response. So this is its frequency response. Which is what we called the MTF before, and this is its impulse response. Okay, so now we want to sort of see, so it's the same thing. I'm representing it either as a time waveform as frequency, and so I want to see what happens when I run it through these two systems. Okay, and the idea is whatever I get out here, its Fourier transform should just be this. Okay, because basically I'm running it through two parallel systems that supposedly are doing the same thing. All right, so that's the intuition that we're after. So let's take a look at that. So what happens is, it turns out any linear shift invariant system just takes a sinusoid, because sinusoids are what are called eigenfunctions, it just multiplies them by a complex number. So all it can do is make them bigger and smaller or shift their phase. So that's all it can do. So in this case, we'll assume it doesn't shift it, it just multiplies it. So for example, if this had some amplitude A1, it comes out with some amplitude B1, A2 came out with amplitude B2, A3 came out with some amplitude B3. Okay? And you can notice here that it's basically, and so if I add all these together, that should be my output y of t, because it's a linear system, so I should just be able to add the outputs together. And so that would be g of t convolved with h of t. Okay, so that's the convolution, just takes those sinusoids, scales them, and adds them up together, and that's my answer. And that's what I will get if I convolve them. Now you notice the way these are attenuated, the first frequency doesn't get attenuated very much, the second one gets attenuated a little more, and the third one gets attenuated the most. Okay, and so this corresponds to this sort of decreasing attenuation in the frequency domain. Okay, so I could also draw this as taking these guys and multiplying it by their respective amplitudes to get this frequency domain representation. Okay? So for example, where this is A1, A2, A3, then these amplitudes are going to be B1, B2, and B3, which is essentially these amplitudes here. Okay? So what it means is that I can either describe things as convolution, or I can just take the Fourier transform coefficients, multiply them by their Fourier transform of the impulse response, and those form a Fourier transform pair. Okay? So that's basically, but for this course, just keep in mind that this is what you'll want to use. You convolve in one domain, and you multiply in the other domain. Okay? So that's the theorem that you'll use on homework 2, problem 4? Okay, problem 4. Okay. So let's look at an application of the convolution theorem. So let's say someone gave you this. This is what's defined as a triangle function. So it has a domain from -1 to 1, and it has an amplitude of 1 at its peak, and it's just a triangle. Okay. So let's say someone asks you to do the Fourier transform of this. So you go, oh, no problem. I'll just integrate 1 minus absolute value of x and multiply it by either minus j 2 pi kxx from -1 to 1. And you could go back and do this, and it might take a while. I know it would take me a while to do this. Okay, but if you take this course, you'd say, well, obviously this is just equal to the convolution of two rect functions. Okay, and therefore I can write down the answer in like 10 seconds, which is preferable to like 10 minutes, right? So it turns out that the triangle function is equal to a rect function convolved with another rect function. Okay, and so you saw some of that last time. On the current homework, you'll do a little convolution on your own, but it turns out that this is true. And so I can just take, I know this goes to a sinc, and I know this goes to a sinc. So by inspection, I can just write down the Fourier transform of the triangle function is just sinc squared. All right, so that can come in useful. So we've talked about 1D. The same thing applies in 2D. If I do a 2D convolution, I just multiply the 2D Fourier transforms. And similarly, if I multiply two functions, I convolve their 2D Fourier transforms. All right. So here's an example of this, which is very applicable to what you'll be doing throughout the course. Let's say we take some object, a g of x, y here, like this, okay, and we convolve it with a, this is, in this case, is a two-dimensional sinc function. So this is a 2D sinc, okay? And from your homework 1, you know if I take something like this and convolve it with something blurry, it's just going to blur out my object, right? So you guys saw that in the homework. You have the cross, you convolve it with a Gaussian, it blurred out the Gaussian. So this is convolution, all right? So this whole pathway here is convolution. Okay, so what it says in the Fourier domain, I know the rect goes to a 2D sinc function. So this is a 2D sinc. Oops, let me write that better. Okay, so the rect function goes to a 2D sinc function. The 2D sinced Fourier transform goes to a rect. And so in the Fourier domain, I take this two-dimensional sinc and I multiply it by the two-dimensional rect function, okay, which is 0 everywhere out here. So what it does is it just keeps the inner part of my 2D sinc. Okay, so convolution in the image domain is essentially zeroing out all these frequencies here. It's basically zeroing them out, okay, because we're multiplying by that rect function. Okay, so that's where it really comes in useful for imaging, that when you convolve in the image domain, you're actually multiplying and typically getting rid of frequencies in the frequency domain. All right. So let's do one example of this, so which comes in really sort of handy when you're sort of thinking about systems, which is, let's say you had, oftentimes, you know, when you're building a system, you might go to different vendors and buy different modules, and let's say each one of them has their impulse response, say H1, H2, and H3. Okay, and you paid like $1,000 for each one. All right, so the whole system costs $3,000. Okay, and this was your input here, and so these are all assumed they're linear shift invariant systems. So the output is just the input convolved with the first one, convolved with the second one, convolved with the third one. So you have this chain of convolutions. Okay, and so what it's saying is in the frequency domain, it's just the frequency response of your input multiplied by the frequency response of the first one times the second one times the third one. Okay, so that's what you have. So now let's look at this example. So here I've got three different systems, A, B, and C, okay, each with their own frequency response, and they each cost $1,000. Okay, and when I multiply all those responses together, I get this is my system response. Okay, but I show this to my supervisor, and he's like, "That's not good enough." Okay, what I really need is for you to give me something with a system response more like that. Okay, and here's another $500 or $1,000 to do that. Okay, so the question, which I'm going to post the poll now, is let's see. Oops. Is that, can you guys see that now or no? Let me see. Okay. Do you guys see it or no? I'm having, it disappeared. Okay, I think it should be good now. Okay, cool. All right. So just tell me which system should you upgrade? It should be A, B, or C? So you have these three systems, A, B, and C. They each have a response, right? You paid $1,000 for each one, but your overall response is not good enough. So now your advisor or your supervisor says, go back and return one of these systems and get a better one. So which one should you go and return? You know, either at Fry's Electronics or wherever, Amazon, I guess, or something. Okay, let's take a look at the response. So nobody likes B, so that's good. The middle one obviously can't be it, right? Because it's either got to be A or C, right, on the end. So right now we have 78% for A and 23% for C. Okay. So let's take a look at that. So of A, B, and C, which is the best system? C, right? It's got the biggest frequency response. So you got a really good deal. $1,000 for that system was a really good deal. Okay, very broad frequency response, which means it has a very narrow impulse response. So it's going to be very high fidelity. Okay, you actually got gypped on A, right? You paid $1,000. The frequency response is like 3 times as bad as C, right? So you should go back and get A, and go get another one of C, right, for the same price. And therefore, then if you think about having 2 of these guys and 1 of these guys and multiplying them together, then you're going to get something. You're going to shift your response from there to there. Okay. The idea is your system response is always dominated by your worst performer. Okay. So even if you had to pay a lot of money to upgrade this guy, it's worth it. Okay. Yeah.
So I'm confused as to how this would ever happen in real life, because can't you just use C?
Oh yeah. So these guys have slightly different functions. Like this might be a preamp. This might be some other filter. So in a chain, you've got different functions. So in fact, you couldn't just go get C. You'd have to go get the better version of A. Like if A was your preamp and module 3 was some other system response. Okay. Okay. Just a few more slides. So one very common example of multiplication when we take a function, say g of x, and multiply it by another function, is when it has the form of, well, in general, but typically, often when it has the form of a sinusoid, complex exponential, or sinusoid, it's given the term modulation. Okay, it doesn't have to be those forms, but that's a very common form of that. And so let's just take a look at this example. We have g of x multiplied by cosine. So this means we're going to take g of kx, and we've got to convolve it with the Fourier transform of this guy. So that's going to be 1/2 delta kx minus k naught plus delta kx plus k naught. Okay? And then what we remember is convolving with a delta function, which you have many examples of on this homework, is just shifting the function. So this is just going to be equal to 1/2. This guy shifted, so it's centered at k naught, plus this guy shifted, so it's centered at minus k naught. Okay? So that's an example of modulation. When you modulate with cosines or complex exponentials, it just shifts the Fourier transform. So a very easy example of this, has anyone here ever used an AM radio? Oh my gosh, a few. Okay, so there used to be these things called, there still are, AM radios. This was the first form of radio. And it's actually pretty cool because actually, on like a stormy night, you can actually use this to like hear stations in Chicago and far away, because these waves can reflect off the ionosphere and you can sort of hear things from far away. So like when I was growing up, I was in Pennsylvania, I'd hear things from like Chicago or Seattle, just way far away, but they'd come in and out. Okay. So anyways, the way these worked was they would take like your waveform, like your speech or music, and essentially just multiply it by some cosine wave. And typically this is on the order of, say, 100, because it's kilohertz, right? Is that typical, right? So in the high kilohertz range. And let's see, 1280. Is that right? Yeah, about right. No, it's probably 1,000. It's 1,000, yeah. It's like 1280, yeah, like I'm trying to think, AM 1490, yeah, okay. Right, okay. So the station I listen to is like AM 1490, so it's like 1490 kilohertz, right? Okay. And basically these create waves that then can propagate. And so our function is g of t times cosine 2 pi f naught of t. So what that does is it takes, if the Fourier transform is here at low frequencies, it just shifts it up to these higher frequencies, which can then propagate more easily. Okay. So that's a form of modulation. For imaging, this is a form where we have a rect function here. Okay. we're multiplying it by this pattern, this wavy pattern here, and so this is the output we get. All right, and then in the Fourier domain, the rect goes to a sinc. This complex exponential, it's probably a cosine because there's two things. You can't really see it here, but the Fourier transform would be like two little dots like that. Okay, so when this gets convolved with this, it just shifts that sinc over, so you have two replicas. You have one here and one here of the sinc function. Okay, so that's what it looks like in the Fourier domain. Okay, and finally, there's the shift theorem, which is sort of just a version of the convolution theorem, because we know that any function shifted is just g of x convolved with a shifted delta function. Okay, and so we can just take the Fourier transform of this guy, g of k, and the Fourier transform of this guy and multiply them together. Okay, and so the basic idea is when you shift a function, you don't really necessarily change the magnitude of its Fourier transform, but you do change its phase term. So this is sort of, this is going to shift its phase. Okay. Okay, and we're not going to go into too much more detail, but just so you have it there if you need to look at it. Okay, so anyways, there's a summary of basic properties here, which you can look at, and then on exams we'll certainly provide this summary as a cheat sheet, and the book also has its own version. Okay, so we won't necessarily get into all of these, but certainly the ones to remember are, very useful: linearity, scaling, separability, duality, convolution, multiplication, and this is sort of a special form of that, and this is a special form of that. So that's basically the things that you want to be comfortable with. Okay, so are there any questions on that? So we've basically just done a very brief summary of the Fourier transform properties. Okay, so what we're going to do now is we're going to shift gears. So Professor McVeigh is going to start the discussion of computed tomography. I'll be here for office hours if you have questions about homework 2 after the lecture. Okay, thanks.